measuring goodness of fit. So we estimate a simple linear regression model. And we call xi explanatory variables because we hope that its variation will explain the variation in y. But can we be more accurate about this? Can we measure how well our x explains y? So let's look at this graph. We have all the data points. So any point here represents a pair of x and y. For example, this point means that corresponding x is many, y is this many. And we draw a line to fit all these data points as well as possible. And clearly, our line cannot pass all these data points, right? So there are always errors. And certainly here we will be interested to know how well, to what degree our fitting is. Yes, we can create a measure, an indicator, a quantity to measure how well our x explains the variation of y. Okay, let's look at this graph. Horizontal axis is x, vertical is y, and this blue line is our regression line, which is y hat is equal to b1 estimate of beta 1 plus b2 estimate of beta 2x. Note that this regression line will pass through the sample average. X bar is the sample average. X bar is sum of x1, x2 plus xn divided by n, which we can write as in a more compact way as this, using this symbol, right from 1 to n, xi. Similarly, y bar is this, 1 over n, sum from 1 to n, yi. Okay, so this regression line pass x bar, y bar. This picks xi. Suppose xi is this value. Okay. Okay, from xi we go up to the regression line. We find a label y, and that's actually yi hat, which is the value of y according to our regression line. Okay, and we know that there's a deviation of y hat from the sample average of y bar. Okay. On xi, our data also have a corresponding yi. That this point is our data point. According to our data, if x take value xi, y should take a value yi, and it has a deviation from its sample average. So yi, deviation from sample average of this many. Okay, that's the deviation of this particular yi from its sample average. And we can see that this deviation can be decomposed into two parts. One part is this. That's the deviation, the component, the part of the deviation that's captured by our regression, or is explained by our regression lines. And the second part is yi, the actual value of y, the data, minus y hat I, the value of y according to our regression line. So the difference of this is the residual ei hat. So this part is not explained by our regression. So it's the unexplained component. So we can see that yi minus y bar deviation of this particular y from its sample means can be decomposed into two components, yi minus y hat. Sorry. Y hat I minus y bar. The component that is explained by our regression plus E hat I. The component that is not explained by our regression. And this is for just one I. So we can sum up all. Okay, sorry. Before summing up, this square them. Okay, so to get rid of negative sign. Otherwise, if we sum them up, positive deviation will cancel out negative deviation. So let's square root them. Let's square them. Okay, we can expand these terms. It will be equal to y hat I minus y bar squared plus 2 y hat I minus y bar times e hat I plus e hat I squared. Okay, I'm going to erase this and write it in here. Plus e hat I squared. Okay, let's sum them up. So now we have, this is the square deviation for one I. This sum over all I from 1 to n. And we can actually show that these terms will be equal to 0, will drop. So let's erase this. This. So this, the left-hand side is the total variation of y from its sample means, and we decompose into this explained component and unexplained component. So this is our algebraic manipulations of the terms. So we arrive at this equality. This is what we call SST, total sum of squares. It's a measure of total variation in y above its sample mean. And this is the sum of squares due to the regression, explained by the regression. And we call SSR, SSE, sum of squares due to the error not explained by the regressions. Okay. So we have this, now we have SST is equal to SSR plus SSE. Okay, now we are kind of ready to define a quantity, like measure this goodness of fit. So this leads us to define a measure, which we call coefficient of determination, or R squared, as follows. So SSR, the total variation that's explained by the regression, divided by total variations, okay? And which is also equal to 1 minus SSE, the total variation that's not explained by the regression, divided by total variations. And you know that this R squared is between 0 and 1, okay? The higher value of R squares, the higher proportion of this total sum of total variations explained by our regression. Okay, if R squared equal to 1, then that's a perfect fit. However, typically we don't have it. We don't have a perfect fit. Actually, if you run regression and find R squared equal to 1, then you gotta be wondering why. Okay, let's compute the R squares for our foot expansion models. So we know SST is sum of yi minus y bar squares. So we have data, we know what xi, yi are, and we can calculate a sample average. We square them, add them up, we get this number. And sum of squared errors, so which is yi minus y hat I, so which is equal to b1 plus, and you know that y hat I is equal to b1 plus b2 xi. We know xi, we know b1, b2 because we estimate, we run the OLS regression, so we can compute the y hat I, we compute the residual, particular residual, then square them, add them up, we get this number. So then calculate R squared 1 minus SSE, which is this number, divided by this number, we get 0.358, which is quite reasonable R squares.